Another important skill for us to have a good connection with in doing a physics class is trigonometry. There's not a lot that I want to review about this, but I do want to get some important facts out of the table. Many of us learned basic trigonometry by looking at the circle. So if one has a circle centered at the origin, it might look like that. This circle may have a radius r, and if we take any particular point along this circle, then that particular point projects down to have an x-coordinate, let's call it A, and a y-coordinate, which we'll call B. As this point moves further and further around, there's an angle that's included here between that little radius and the x-axis, and that angle starts at 0 and sweeps up larger and larger until it gets all the way around and becomes 360 degrees. The sine of that angle is defined as a ratio. It's defined as b over r. The cosine of this angle is defined as a over r. The tangent of this angle is b over a. There are other trigonometric functions like the cosecant and the cotangent and the secant. These include things like secant theta is 1 over cosine theta, or cosecant theta is 1 over sine theta, or cotangent theta is 1 over tangent theta. But the important thing is to remember this acronym. Which I think I have right. So the sine is the opposite over this radius, which is sometimes called the hypotenuse. The cosine is defined as the adjacent side over that hypotenuse, and the tangent is defined as the opposite over the adjacent. Now, it's generally true that you can plug angles into these functions, 20 degrees, 50 degrees, and so on, and compute what is that value for cosine of theta or sine of theta. But it's helpful to have a little bit of a memory about what some of these things are. So for example, if theta is 0 degrees, or 30 degrees, or 45 degrees, or 60 degrees, or 90 degrees. These are some angles for which it's useful for you to know the values of the standard trig function. When theta is very small and goes to 0, then this side b goes to 0, and the sine of that angle is 0. However, this adjacent side, as this point moves around and around to the circle over here, the adjacent side becomes just the radius, and so this cosine becomes 1. The tangent is just defined really as the sine over the cosine, and so this becomes 0. At 90 degrees, the opposite is true. At 90 degrees, this little vector, or this radius, is moving all the way up to here, and it's located right at that spot, top of the circle. In which case, side b is equal to r in length, and the sine is equal to 1. cosine will be 0 because this location A moves back in toward the origin, and actually the tangent becomes infinite. In between, how do we remember how to calculate these things? Well, we use Pythagoras' theorem, and we remember that for any of these angles, this coordinate a squared plus that side b squared equals r squared, and that's because this is a right triangle. And that allows us to find out things like this is 1 over root 2, this is 1 over root 2, and this is 1. And for 30 degrees, the sine of theta is a half. The cosine of theta is root 3 over 2, and the tangent, which is sine over cosine, is 1 over root 3. 60 degrees looks a lot, it's very similar to 30 degrees. It's just that instead of being down here more, that point being like over there, it's flipped over on the other side of 45 degrees. So these two things switch places. This becomes root 3 over 2, this becomes a half, and the tangent becomes root 3. So I don't expect you to memorize the values of the trigonometric functions for all possible angles. In fact, it's really hard to do that. But for some of these key angles, it's very, very useful to be able to call those up from memory. Let's go back to our circle again. We know for a circle, it has a circumference of 2 pi r. That is, if I take this angle of theta and move it all the way around to the point where it gets over to here, and the angle is 360 degrees, then there's a linear relationship between this circumference and the radius, and that's just related by a factor of 2 pi. I'd like to define a more general relationship that if I had some other angle theta that's not 360 degrees, instead I had something that looked like a pi wedge, like I've drawn up there, I'd like to be able to write down some sort of again, a linear relationship between this length of this outside of the wedge and the radius r. Clearly this side, this length, gets large if r gets really big, and it gets big if theta gets really big. Well, this relationship works as long as theta is measured in what's called radians. One revolution we know to be measured in 360 degrees, but it's also equal to 2 pi radians. So this expression works as long as I measure theta in this new unit. If theta is less than 2 pi, then that means I have a wedge like so. If it gets up to equal to 2 pi, then I have one revolution, and I'm back to 360 degrees, and I get what I expect, that the circumference is 2 pi r. So 0 degrees is 0 radians, but 45 degrees would equal what? Well, 45 degrees is about 1/8 of one revolution, and that's pi over 4. 90 degrees be pi over 2. 180 degrees would be pi. .30 is a third of 90 degrees. So that's pi over 6. 60 degrees is 2/3 of 90. And that would be pi over 3. And so on. So it's useful to be able to convert back and forth between this new unit of radians and the old unit of degrees. If we were to graph these functions, it's useful to think about what they might look like. So I'm going to graph on the vertical axis y, on the horizontal axis I'll graph theta, and I'll do this in degrees just to make it easy on ourselves. This might be 90 degrees, 180 degrees, 270 degrees, 360. This would be minus 90 degrees. So the sine function starts out at 0, but grows larger. It does something like this. And at 180 degrees, the sine function goes to 0 again. At 270 degrees, it actually goes negative 1 because the opposite side is pointing straight down. And at 360 degrees, it's back up to 0 again. In other words, you made one full revolution. At minus 90 degrees, I'm down here at minus 1. So that might be a graph of sine theta. The cosine of theta does the exact opposite. It starts out at 1. At 90, it goes to 0. At 180, it equals minus 1. At 270, it's back to 0. And at 360, it's back up to plus 1. So these two graphs look very similar to one another. They're just shifted over. The tangent is a little funny. The tangent is the sine of theta divided by cosine of theta. So it starts out at 0. It's 1 right here. And it just keeps on going up. So at 90 degrees, it's infinitely big. At 91 degrees, the sine of theta is still pretty close to 1. The cosine is very, very small, but it's a negative number because I'm over in the second, what's called the second quadrant. And the graph looks something like that. And I have these dramatic arcs that look like so. So the tangent of x, or tangent of theta, is constantly going between minus infinity and plus infinity. And it goes through 0 at multiples of 180 degrees. 0, 180, 360, and so on.